Hey everybody, thanks for coming to the fourth and final session of the kernel track at Fossy. Our next speaker will be Ben Dooks, who works at CodeThink, and he's here to talk about introducing Big-endian to RISC-V.
Yep. Okay. So let's wake you all up. Everybody here knows about RISC-V? Good. Big-endian? Yay, we're actually going to be... So this is a little bit about our adventure into the RISC-V Big-endian. Introduction, we'll go through some of the concepts anyway, go through what the work we did looking at it, how it works. So, introduction. So if you probably don't know, CodeThink, we're an open source consultancy based out of Manchester in the UK, about 100 people or so. And for this project, it's myself, and we had 3 other engineers working on this on and off. So Lawrence Hunter, Rowan Richmond, and Nazar Kazakov. And they're pretty much everybody's done the work on various bits. So about me, well, you can see me, so I'm going to put a picture of some goslings because I think that's better. I certainly don't look as cute. So I'm senior engineer and now fellow at CodeThink. I've been a long time open source contributor. As if you've been to a previous panel, I've done kernel work across for people like Samsung, did some work with I2C maintainer, drive-by patching of various other projects. So we'll go through the contents. We'll talk about quickly what is Big-endian, how RISC-V does it, what we decided on the software stack for actually doing the work. We'll go through the issues, debugging, future. So, firstly, endianness is like the way that order data values are constructed in memory. You can sort of think about Big-endian being left to right and little-endian right to left. So we have a little diagram here, and we'll talk a little bit more about this. So why would people do Big-endian? Well, architectures like PowerPC and other very dead systems used to use it. Networking protocols often use Big-endian representation in their headers. So like TCP, UDP.
I'm curious about that overhead. Is that measured by any chance? Do we know if that's
So there's a question about overhead. We'll get into that a little bit. We do know that there's definitely people interested in doing this, but we'll come to a bit of how difficult this is to measure later. But we haven't done any good benchmarking as far as I'm aware yet. So many newer systems are now little-endian. It seems that x86 chose it because it makes their life easier. And of course, x86 achieved dominance. So we're stuck with little-endian. So why would we be interested in this? Well, up until recently, RISC-V was little-endian only. And by latest, I mean 2023 specification, they added some endian control. So that was version 1.12. I think actually it was initially published in 2022. But silicon vendors are not quick to adopt anything. So we talked about a little bit about what Big-endian is and how RISC-V hasn't done it yet. So how does it work for RISC-V? Now, RISC-V has a number of control status registers that the cores use to control how they're working. So the M mode has a control bit in the M status CSR, and this is called MBE, which is added to say this is the endianness mode that the M mode is in. And again, you also have similar for the S mode of 36, shows which mode S supervisor is in. And it goes all the way down to the user mode, which is bit 6, which is both in S status and M status, because really the status registers sort of stack up, and you each sees bits of the lower modes. So the endianness only applies to the data. So you don't have to worry about your instructions changing endianness if you happen to swap. The definition that RISC-V took is that your instruction stream is always interpreted little endian. So with the CSRs, you can therefore change your endianness at runtime. However, you can't change your own mode endianness. You'd have to ask something else to do it, because you can't prod your own endian status. And one thing that they did, which is really nice, is the MMU follows the endianness of the supervisor mode. So M mode does not have any MMU. It just has some basic protection, so you don't care there. But it makes it easier, so you don't have to think about swapping your data endianness when you're building your page tables in your operating system. So that's useful. So for our project, what we're going to do with our definition of done. So we're not going to do everything for Linux, so we went for small Linux userland. Before we even started, we checked that GCC will build Big-endian RISC-V code, because absolutely we do not want the headache of dealing with GCC. It turns out that having talked to some other people, there is work to make this work for Clang as well. So Clang and LLVM will probably be getting Big-endian RISC-V support at some point soon. We'll use QEMU because nobody's done this, so nobody's actually shipping any silicon. And we'll use OpenSBI to get the boot going, so we'll need to do some modifications there to get the endianness set up. And then Linux, obviously the kernel may need some changes, and really just to build something simple, we went for build root. So first thing we really needed was something to actually run some Big-endian code. So we don't have any hardware, so let's use QEMU. So our first goal had to be to start adding these bits, the status registers, to make them writable. We initially just made everything follow M mode, just easier, but after a while we added the SBE and UBE flags, and then the code that changes the endianness based on that. So once we got the CSR rights, we can then go, okay, if this is updated, we now need to change the context that QEMU is using to run the code. So we have a new context field called BE_data, which also requires then the translation block that QEMU is using to create native code from this to also have that. Again, S-state is, as we said, is a partial view, so we just really needed to change M status for initially. So as you say, to get a QEMU working, basically we have to go through all the memory operations going, okay, we've got this new BE data flag to say we're in Big-endian. Thankfully, QEMU already knows about how to deal with endianness in data, because it does already support things like PowerPC. I can talk about it here because I'm not in any RISC-V conference, but ARM has also been doing this for some time. So they've had a very similar way of tracking, allowing endianness configuration. So that was a thing. So we didn't have to worry about that. And it turned out actually QEMU uses some flags for its memory operations, so it was easier to actually store the flags we would pass in our Big-endian data. It also turns out that Linux does not work very well if your atomic operations aren't in the right endian. It turns out they use it a lot for their things like spin locks. So even if you're on a single core system, yeah, it's a bit of a pain. It also, we had to ask about the FPU. Wasn't clear if the FPU followed the endianness, but it does. So we also altered the FPU at the same time. And the only other really annoying thing was the page table walker. So we went through that and did the similar thing of, if we're in Big-endian, make sure that the page table walking code in QEMU follows that, because it has to fetch data and create its translation tables. rather like just a real core would. So we got that working, decided to also then add the execution mode selection, which again was fairly easy to do. I mean, it's not a huge set of updates. I think here 14 files and about 120 changes. So that's not awful, but at least gives us a base to work from. So our software stack, so we a lot of the times we're running into another issues that a lot of the software builds assume little-endian. So things like build root, UC libc, they'll need changing for putting the correct compiler and linker flags in. Thankfully, that's fairly easy to do, but you have to go through and do it. The next big problem is that a lot of the I/O for memory mapped I/O is going to assume little-endian data, so we do end up having to certain places like the kernel and OpenSBI do some swaps on I/O. Thankfully, Linux and OpenSBI tend to concentrate all these via a set of macros that you can go and change, and given quite a few other architectures do the same, we found that was quite easy to change. And then instructions, they're little-endian, right? This is a slight problem if you say need to do introspection or code modification at runtime. You have to work out whether you need to swap your data or not. And there's a really weird one at the end, which is the people doing hand assembly of code. And we'll talk about that in a little bit. So for OpenSBI, this is the monitor mode software, like a BIOS in your system. Really, it was a very little change. We updated the compiler flags, added a little bit of code to say, okay, now we need to swap. We need to set these bits for the Big-endian in the various modes. So we had an option to that to say, okay, at startup, we're going to switch to Big-endian, and we'll switch everybody else to Big-endian while we're at it, because we didn't bother putting a call in to say switch to the endianness. So that added an option for not only M mode, but S and U modes as well. So basically, we're going to force everybody to work Big-endian. I/O code, that was quite easy to do as well. Did we even need to do this? Well, it turns out because the endianness in the registers really doesn't matter, and most of the communication between SBI and the lower levels are just done mostly through registers. We could have probably just run M mode in little-endian, but we did it, and it was quite simple to do this. So, and we have a couple of little examples here. Hopefully, people can read them. It's just basically changing OpenSBI's kconfig to add some bits, and then in our case here, load the constant for mstate as MBE, and then just call the CSR, do the instruction to tell the system to set that bit. Again, we also had to make sure that any other hearts that were brought up or reinitialized were also set up like that. So, why did I talk a little bit about instruction endianness? Well, it turns out that because often people are building the system with older tool chains, they don't often produce all the right instructions, so people hand assemble stuff, which is great, except now we have a problem that our linker is going to swap the value, that word, and produce something that is not a legal instruction. Thankfully, somebody thought about this and added a .ins and assembly directive, which also has the useful byproduct of telling the output that this is actually an instruction, not a piece of data. So we've gone through some of the changes for the code. Things like UC libc, they also do need to know a little about the endianness. Thankfully, GCC has some defines you can use, Why on earth UC-libc just doesn't use these directly is very probably these were done in a very, they've been changed at least once in GCC's lifetime. But this basically says for anything that cares about byte ordering, what the byte order is. So that's used, and we'll go through that in a second. When you have data decomposition, so subfields of a word might move around depending on the endianness. So the code may need to adjust shifts or how the data structures are accessed. So the example here is that if you're in, depending on your endian, you control which way round you load from the TCP header to say, get the bit I wanted from that header. Again, we haven't gone through all the acceleration code. So we did cheat a little bit in cases where we just said, just use unaccelerated code. It was just a lot easier. So as I say, for when we went into the Linux kernel, there are some optimized code in there. So just avoid dealing with that by going, no. So the biggest actual changes were mostly going in and looking at the places where instructions were modified. And it turns out the kernel does quite a lot of this. There's things like static branches. So if you have a branch that's resolved at runtime, that code goes through and alters instructions. So you need to go check it. And if you don't get it right, your kernel does not work. The instruction trap code, well, that actually looks for things like the bug macro, which turns out just to emit an illegal instruction, and then it traps it. If you've played with the Berkeley packet filter, that code actually has a just-in-time compiler. So that has two problems: of it produces instructions and it deals with byte-ordered code, because obviously it can either deal with native data or it can deal with network data. So, and also kernel, kprobe, and uprobe. Those are probes which also cause instruction modifications. I don't know whether we ever completely tested them. We'll probably talk about that in a bit. Oh, and of course, then we got reminded that there's a hypervisor involved, which adds two new execution modes. So a little bit about the kernel hypervisor. So if you're using KVM on RISC-V, there's a new H status control and status register, and that's been extended to have a VSBE control, which is your virtual supervisor mode endianness. Again, if you're doing page table walks, the hypervisor does it in the host endianness, and the layer that does the translation for the guest is done in the VSBE mode. And also then you've got the V status for UBE, which is the mode for the U mode in the hypervisors. So we did update kvmtool to allow you to say, okay, now you can create your guest and you can control those bits as you turn it on. We also found some interesting problems with kvmtool's endianness, which was a bit annoying, but it turns out most people have just been doing little endian. So we've not really gone much into this, so it's not been very well tested. And I think we still need to probably put out a request to comments to say, is this going to be the right way to do it for RISC-V? Because obviously this is going to be an addition or a change to the KVM ioctl controls, to which means a userland API possible breakage. So by default we just go with the host's endianness for the guest. So I'm not sure if you can see this. This is a quick diff stat from the current kernel patches that we've done. So it's about 33 files have changed, 215 insertions and 73 deletions. So as you can see, it's not actually a huge amount of code. Unfortunately, it isn't exactly not invasive, because we are touching all sorts of the core kernel to do things like, okay, dealing with the instruction endianness, I/O swapping, and let's not even go into the idea that you could also change your I/O endianness depending on your system. I think people have in the past done just purely Big-endian RISC-V by just doing everything it being Big-endian, but these people are not being supported by an upstream kernel. So a little bit about how we went through some of the debugging and testing. So we said we were using QEMU. We did a little bit of example code using GDB into QEMU to actually see how it was going. That got us an idea that how we were getting the code was progressing. We quickly decided actually let's go for a full kernel boot. We quickly found that Linux requires the AMOs even on a single processor. So AMOs are the atomic memory operations. It's like, okay, can we be bothered to remove all these AMOs, or let's just fix the things? Basically, it's the locking, which is the problem. So we ended up just fixing AMOs. It turned out not to be a huge change. So our first fun problem, RISC-V does an unaligned access test at startup to work out if these unaligned accesses to memory are efficient or not, and we were getting faults. Now, obviously this worked in little-endian, so why on earth did we, when changing to big-endian, did we get a problem? We could probably just configure this out, but I was thinking, okay, this up here, this is a weird problem, and what on earth is going on? Could this be an underlying issue in our code? Could GCC be wrong? We'll talk a little bit about one or two other issues. So we went in, had a look at the code. Well, the disassembly looks okay. It's doing a store 0 into register S0, which is the stack frame. So this should be working. The compiler should be managing the stack frame for us. The address looks like it's valid in kernel memory. And we said it works in little-endian. Why on earth is it not working here? It turns out we had a quick look at with GDB. The address is not valid. It's outside the page that the stack frame is in. And we're going, okay, well, that's weird. So, okay, we could just go through, run this single stepping. We disassemble the code. That looks okay. I ended up going, actually, let's do a quick diff of the object between the two compiled versions. Obviously, they should be really similar because it's not doing any I/O code. It's not doing anything weird. And I don't know, you can probably see at the bottom, same code, different output. So left is little-endian and big-endian is on the right. But on the little-endian side, it does this fence and then a load. On the right side, we get a NOP and an add with S0 stack pointer 912. What's going on? So we decided to do disassemble, and you can do disassembly with source, and it very, very cleared that this was a problem when CPU relax with a hand assembly. And it turned out we thought that any hand assembly issues would have just provided a unknown instruction because it's been byte swapped. It turns out in the compressed instruction set, it's actually a completely different but legal code sequence. So the RISC-V pause is this 4-byte value, which is a fence in little-endian, and that's the correct thing it's doing. It's basically saying, okay, relax a little bit, cause the processor to do something that may synchronize up. So the correct fix here is to change that to the .ints, and they could have made something that was actually easier to say. But yeah, so that was the change. Fixed that, and it worked. So we had a thing. So we'll talk a little bit about the future and probably some more developments. We have a kernel that's booting now. We had a very simple user land. It turns out that we had some real problems with GCC and glibc, but UClibc works enough with some very simple patching. So other future things. Now, when we started, there was no instruction that would help us with byte swapping, but it turns out that actually one of the extensions called ZBB actually has a reverse instruction in it that reverses an entire word, not a subword, just an entire word. But newer GCCs can use this for byte swapping. Most modern cores, and I think Ubuntu is going to require this, will have ZBB with this extension. Turns out the kernel didn't use it, but somebody has now put out a patch set, I think now on revision 5 for doing this, which is really annoying for me because I started working on this, read the RISC-V list and went, I spent all morning doing a patch for this and somebody's just submitted. You know, I mean, it's very possibly great minds think alike or something, but, you know, it's interesting, but people are thinking about this. We did say a little bit about how efficient this is. So we did a quick test bench of the BREV 8 on a Vision 5 board. Turns out for actually the UINT 16 is not actually that much faster. The code is really similar. For 32 and 64-bit, it does make quite a big improvement. Whether this is going to be as big an improvement on the kernel because it's going to use the alternative framework, that's going to be interesting to see. But this is a really simple test bench, just doing some really just doing tests in user space. So, I mean, for a code diff, the left is what GCC would output normally for. Oh god, this is the with. Oh, I can't remember if this is the 16 or 32-bit, but that left is the non-optimized. Right is the ZBB version. So you can see it's really similar code length for that. Oh yes, so it's Rev 16. I put it on the thing. For the Rev 32, it gets a lot. It's a much more of a win because the sequence is not is still a BREV 8 and a shift, whereas the stuff which would move it around by anding and oring registers gets a lot longer. So the next thing we thought about is that given that nobody's doing this, there's an open source implementation of a RISC-V system on chip called CVA6. So this is a open RISC-V core from the Open Hardware Group. It is backed by one or two other quite big companies, but it fits in a modern FPGA. It's written in mostly system Verilog. You can have an argument about what's better, but you know, that's what we've got. So we did a little project to see if we could do the update the status bits. We have actually managed to get something working now. We've actually booted Linux on it last week, but I haven't updated the slides. However, the annoyance it had multiple points where it does load and store, and we're not sure if the extra logic is pushing things around in the FPGA in a good way or not, which is annoying. But if anybody's done FPGAs, you change some little bit and it radically changes the layout of whatever. It does seem to have, at least we think, still fit within the timing. So we're probably going to put out this as a request for comments. Whether CVA6 people are going to take it or not, we'll find out. Apparently they're already considering other layout changes in their code, we may end up having to wait for them to do that. But on the right is one of the it's a Xilinx dev board from Digilent. I think this is one of the really annoying things about FPGA development. None of the open tool chains will touch this, and the Xilinx toolkit for building FPGA code is eye-wateringly expensive. The dev kit does come with a license for a year. It may well be cheaper just to keep buying dev kits to get the license. We would, I think, we very much considered whether we could do an open update to some of the Yosis and things like that. However, the system Verilog front end for them is a little bit out of its depth here. It turned out we just caused it to segfault, which is really annoying, but we have to work with what we've got. And then I was giving this talk for the RISC-V Summit, and somebody sidled up to me and went, you said you didn't have a core that did this. Well, congratulations, we're doing this. So MIPS have very nicely engaged with us to say, they are actually doing this new core called the i8500. Their SDK isn't quite released yet. The software URL is not yet available, unfortunately, which is really annoying because I'd like to get to look at their code. But we've talked to them, and they're getting their side in order. They're the people doing LLVM Big-endian. So this is actually really great to say, we're doing something that people actually might want. So I say this is some slides from MIPS. So they're doing some stuff around 64-bit, real-time, network, system on chip type stuff. I won't go through all of them, but they will have a development kit out as well. That is a much bigger FPGA. So I don't know how much that would be, whether that's going to be anything that a end user is going to be easy to do, but they're doing very similar to us. They have the same sort of simulation, tool chains, software stack. So that'll be very interesting. So what problems did we have? Well, really weird is that up until, and it's now fixed in GCC 15, building glibc would actually segfault GCC. No idea why, and if you've ever tried looking into debugging issues with GCC and its internal segfault, let's just not go there. I have better things to do with my time. So we haven't done any testing with buildroot and glibc yet, which is a little annoying, but UClibc will build most of a simple root filing system. So for instance, we had to update kvmtool to build without glibc because it had a dependency on that. Again, the muscle library had problems. We don't know why, and we just decided not to deal with that. I think number 4 is now solved. I think we got the K probes done, but again, this is like an R&D project for us. We're not going into huge amounts of testing. So we'll talk a little bit about upstreaming efforts. So we have RFC patches out. We sent to the kernel list and QEMU list. The response has been underwhelming. The QEMU people haven't really engaged, and we think we are going to put a third round of patches out now that we've done further testing, and I think MIPS have also been playing with our QEMU tree because it looks like we're probably slightly better off than they are with that. The Linux kernel was basically this looks like work we don't really want to do because nobody's doing it. I think we're going to go back with a second round of patches, updated, because I think our initial ones were against 6.13, and I think we're now 6.16. I've done some rebasing work and fixed the problems, so we now have a better patch set, and hopefully if we go back and go, look, we have 2 implementations that do RISC-V Big-endian now. Let's get that, get moving on that. I say, also somebody's already set the ZBB patches up, which is interesting, so we'll be able to do some better benchmarking. I didn't ask MIPS whether they've done anything for their promotional work, but we've basically been doing functional tests and assuming that everything is now better for networking in Big-endian. Obviously, we've got some conference talks, so we'll be spreading the word. I don't know if we really need anybody at the moment to sort of get involved, but if people like playing about with low-level RISC-V code, feel free to have a look at the accelerated like string functions and see how difficult they would be to change. So that's roughly where we are. So as of a month or so ago, we pushed up a kernel, QEMU, build root, patch set to our GitLab. Is it GitLab? Yes, it's GitLab. I can't remember what we use half the time. There's a nice QR code there and a URL. That also has a project log of what we've been doing. And I think we've got all the talk slides up there. This slide set is fairly much the same as the talk from Open Source Summit North America, but it's a larger version than the RISC-V Summit because those were only 20-minute talks, so we didn't go into as much detail. So yes, you're welcome to have a look at those, download the code, play with it if you actually want to. So thank you very much. It's been interesting being back in Portland. Not been here for a while. Also, I'd like to thank CodeThink for, well, both sponsoring this conference and for sponsoring some of my travel expenses for coming here. If you have any questions, I think we've got some time, like 5 minutes or so for. So I know I'm going. So
thinking about like practical applications for this, would this be in like a network accelerator card? And then what would you think about some of the more far out applications that, like, say you have this network accelerator card, it's a Big-endian, it has a support cord that's little-endian, and then it's talking to a CPU that's little-endian, that's running a hypervisor that's Big-endian.
Yeah, so the question is basically around like network accelerators having Big-endian and talking to various other things. Yeah, that's probably going to be a big headache. The use case for networking is fairly clear, given that a lot of the protocols are Big-endian. What I didn't touch on is there are people with legacy applications where really rebuilding them to deal with Big-endian data in a little-endian system is really not easy. So they would be better. They would be better off running a purely Big-endian system. We did that a while ago for the ARM case, and it turned out that it was just it was much more efficient at runtime. It was just easier to convert the entire database over once and then deal with it. I think I've got most of your question, but yeah, it's at least, I mean, as a caveat, as an extra, at least nowadays things like glibc have good conversion functions to say whichever code you're building, you can say I want to output a little-endian or Big-endian value. So a lot of the times when you're doing driver work, you have to think about what your hardware is looking at. So some hardware you can't control the endianness, it's always in little-endian. you'd have to write your like DMA descriptors to memory in Little-endian. So, yeah.
So were you saying with CVB that the byte swapping instruction can give you some of the gains that you would get from doing the whole Big-endian thing?
So yeah, the question is about ZBB. It does give you definite gains, especially if you're doing quite a lot of work with 32 and 64-bit. And the TCP headers they do sequence numbering in 32-bit Big-endian. So you would get some gain. The best gain would be if you could ensure that your Linux kernel was set up to do ZBB only and not have any alternative code where it would have to swap. If it decided at boot time there was no ZBB, then it would have to patch in code to do the shifting. Now, it looks like ZBB is going to be mandated, and therefore pretty much going forwards a lot of distributions like Ubuntu are just going to say you have to have this. So that would probably be, and GCC does know how to do it. So if you say to GCC, I'm building for something which has ZBB, it will output the code to do it with BREV, which is a little bit to a lot of a win. It's still not like a single load win, but it's 2 or 3 instructions to shift and then.
Right.
Because annoyingly, the BREV is only on a complete 64-bit word. It's not like, I think ARM has a swap for 16 and 32, if I remember correctly. So that's even more efficient. So.
Because it seems like it would maybe be easier to just focus on the extension, right, than to change the whole representation. I mean, I guess it depends on the core designers.
Yeah.
About it.
So the addendum to that is it might be easier to look at the extension. As I say, it wasn't guaranteed before RVA 30, the RVA 23 standard. Also, it's not as fun a research and development project.
Sure. Yeah.
I say we've done this as part of just let's get some of our newer engineers both interested in hardware and get them some get them experience with playing with upstream. Now, 1 or 2 of them are getting a bit frustrated about not having a lot of response to their stuff, but we've got some talks, we've got people going to conferences, we've got some young, probably now not junior engineers interested and worked on open projects. So the kernel stuff is quite a lot of my own work. The QEMU code is myself, Rowan and Lawrence, and Nazar and another guy we've just got have been working on the CVA6 Big-endian stuff. So hopefully we'll see some movement on the CVA6 side once that's cleaned up and submitted. I'm assuming that we'll get a round of reviews and then end up either having to do some more work. But it's at least the CVA6 people sort of engage, even if sometimes the responses are basically leave it for the moment. We had another interesting funsy with some of the older CVA6 cores have a bug in their floating point dirty state tracking, which means you can't rely on the core to tell you whether the FP state you loaded has then been modified. So it makes you wouldn't think that was a problem, but the CVA6 release has a game of Tetris in it. If you hit the bug, it stops randomizing. You get the same bit all over again, and that's going, this is the easiest game of Tetris I've ever played. So yeah, as I say, this is, until MIPS came along, was very much a completely theoretical thing. We thought, let's do this, it's in the spec, and we'll just play about. It turns out to be a bit more work than we were expecting, but we actually, I think, got a reasonable result. So, any further questions? I believe there's an event tonight I may well be keeping you from. I say feel free. I've also got some cards with the project URL on if you want. And yeah, I'll be putting slides up and stuff. So I think if there's no further questions, we can close out.